Let's get started. I would like to introduce Kaizen's own Chuck Sexton.
Hello, everyone, and thank you for joining. I appreciate it. Thank you, William, for the introduction. My discussion or topic today is on how to clean carbonaceous soil. It's one of the more difficult contaminants to remove in both new parts and also in remanufactured parts. Those of you familiar with burned-on carbon, this is sort of what it looks like. And when I'm in plants, over the years, I'll walk through and rub my fingers on different parts before washing and sometimes after parts washing, just to see how much carbon is on the parts. And it's very telling. Carbon smut includes various forms of amorphous carbon obtained through incomplete combustion, high heat exposure of plant, animal, and other organic substances. Amorphous, the key word, meaning without a clarity defined shape or form. I did a little bit of research on the internet to find this definition because most of us know what carbon smut is, but the distinction they made was that graphite is crystalline, and of course coal would be carbon smut is more of a paste. And those of you familiar with carbon smut would guess this, I think. These are examples of carbon smut or burned on carbon on parts. The pictures on the left show parts where the carbon is burned on. These are remanufactured engine components. It's pretty obvious where the carbon comes from there. The carbon can also look like the parts in the middle, where if you stand over them, you might not see anything. But if you rub your fingers on them like I do, you'll see the carbon, or take a white paper towel or cloth. The carbon on those parts, and these are friction discs for transmissions and brakes, it's actually applied during the gear shaping process, which forms the teeth on these parts. Carbon smut comes from many sources. Machining is one of the most common. You often wouldn't think that, but in these different milling operations, you can see here from this chart, machining temperature in milling at high cutting speeds, steel's the hottest. So where the tooling meets the part, you can get up to localized temperatures of 1600 degrees C. And you can see with the other metals, it gets also very hot. So even the lubricant carbon within the coolant becomes carbonized or charred. Deep draw operations and forming, which I show a couple of different examples of here, also form carbon onto different parts, excuse me, from the drawing oil. Here's a chart that shows in a press of this type the temperatures where the die heats up after 30 parts or so. The temperatures where the die meets your substrate part can reach as high as 180 degrees C. And there again, we're making carbon. Remanufacturing's pretty obvious, I think. I mean, temperatures get very hot in automobile engines. These are automotive parts, except for the bottom right part, which is a wheel hub for a jet aircraft. Again, temperatures of, for example, the exhaust manifold in an automobile are from 300 to about 800 degrees C, forming carbon as you see here. Other, I think, pretty obvious examples are welding, laser welding and cutting, brazing, soldering, wire EDM. Just to mention one, in welding operations, often people will use these anti-spatter oils. So any weld spatter that drops on the part, it's obviously extremely hot, and where it meets the oil, it carbonizes the oil. When you get involved in a process improvement or development of a new process to remove carbon, we ask three questions. More, but these are the main three. What are the soils? What are the parts made of? What is the current or desired process? I show this slide because my first question was, what are the soils? And I'm talking about carbon in this presentation, but it's very rare that you only have burned on carbon on parts. You can see these remanufacturing parts. I mean, there's often heavy oil, and same with deep drawn parts, heavy oil that you need to remove. The part on the right here is a crankshaft, which even has iron oxide on it or rust. These are parts that we clean now. And coming out of, I think it's about a 2,000 ton press, these parts are quite hot And as you can see, the part on the left, they're covered in oil, and underneath that oil is the burned on carbon. So you have to remove everything in these operations. The second question was, what are the metals? And we asked this question because we need to choose the right chemistry that is compatible with the different metals. And I break them into three categories: aluminum, steel, and then the yellow metals, copper, brass, and bronze. This slide shows general process flow for a cleaning process. So the right 2/3 shows the aqueous process, which is commonly run for cleaning. It usually involves combinations of spray and immersion. There's often one or two washes followed by a rinse at the end, which can contain an RP. The blue box I have shown at the beginning is for vacuum degreasing, and that's an excellent process which uses two different solvents, a hydrocarbon and a modified alcohol, which is excellent for removing the heavy oil and grease at the front end, and then really going after the carbon with the aqueous process. The difference between aluminum and steel, again, is the chemistry that we use. With steel, we use a high alkaline cleaning product that contains sequestrants or chelators to remove oil, grease, and carbon. The second type of product we use is a somewhat similar product, but one that's heavily fortified with corrosion inhibitor, so we protect the steel. The third product is an acidic cleaner. Unfortunately, the alkaline products aren't very good at removing oxide, and often with these parts we have oxide to remove, so the acidic cleaners do the best job there. For aluminum, we use a lower alkaline product, usually with inhibitors to protect aluminum and brass and copper. A mild alkaline product with chelation. The second product is a mild alkaline cleaning chemistry with corrosion inhibitor, and that's for customers who want to protect brass and aluminum for usually more than 3 months. And then an acidic cleaner to remove, in this case, aluminum oxide, copper oxide from those parts. It's a different acidic cleaner than what we use for steel. Just some examples here of the spray systems that we get involved with. Cabinet spray washers, conveyorized spray washers are excellent for removing the original oil and grease on these parts. And with the right chemistry, they will also remove a fair amount of the carbon. And then the immersion systems, where we'll remove the rest of the carbon with an immersion product. The best process, once you've gotten down to where what you've got left is carbon, the best mechanical process is ultrasonic agitation, ultrasonic immersion with some type of part movement, either a vertical agitation or a rotating basket with the right chemistry. A couple of slides on the vacuum degreasers. There are two different solvents, modified alcohol and hydrocarbon, which again address the oil and grease on the front end, and they're often used at the very end of the process as well to meet millipore specs. One of the solvents, the modified alcohol, is polar. The hydrocarbon is nonpolar. These are some examples of some equipment that are used in this application. That's all I'm going to say about vacuum degreasing. We have a tech-to-tech presentation in November where we will get into much more detail on this process. When you're looking to improve your cleaning operation, to remove carbon or develop a new one of the best first steps is to test. We always like to test when we're removing carbon. These are some before and after pictures of different applications, lab tests, where we use full-scale equipment. We like to do the testing because carbon is so difficult to remove. We need to prove it to our customer, but also to ourselves. The second step usually involves a plant trial. Once we've got a good process that we think we can improve on what you're doing and meet your specs, then we move directly to a plant trial. These are a couple of slides here on some different plant trials that we've done. In this particular one, which is remanufacturing, we were able to double the bath life out to 20 days, which made a big difference. Here's another application. Again, this one's I'm showing reman because these are some really difficult carbon removal applications. We were able to double the bath life here, and often with carbon, you've got someone or some automated blasting machine that's removing the very, maybe last 5% of the carbon. And in this application, we were able to reduce the time required per engine head from 20 to 25 minutes to less than 5 minutes. Some other applications that we've gotten involved with on plant trials, and you can see that the results are usually, pretty obvious. Finally, the process goals for carbon removal are lower costs for the parts cleaning process, which is a pretty obvious one, improved carbon removal, improved cycle time, reduction in manual blasting, improved corrosion protection, and improved worker safety. That's my last slide. Now I'll turn it back to William. Thank you very much.
Thank you, Chuck. If you'd like to discuss this topic further, please contact your local Kaizen representative or send an email to tech@kaizen.com. And we will have one of our cleaning experts schedule a follow-up with you as soon as possible. Again, we thank you all for joining us today, and we hope to see you again soon. Stay safe, stay healthy, and have a great day. Stay healthy and have a great day.